Okay, I think we can start now. It's 8 o'clock. So, so last time I told you for sine, if we have a sine wave, the x-axis can be time or it can be angle. Okay. So in case of time, so it's going to be sine t. If also we can make x-axis angle. In case of angle, you have here the whole period is actually 360. Okay, so that means here it's 90, 180, 270. Okay, and I told you in case of angle, what we are gonna do, we're gonna say sine omega t. Okay, and omega actually is 2. I just want to explain how I converted time to angle. Okay, so it's very simple. You can see t. This is the period t. So t is equivalent to 360. Is that okay? Half t is equivalent to 180. 1/4 t is equivalent to 90. That's what I did. So I'm gonna get the ratio of the time. So this is actually what omega t is doing. So omega t means 2 by f t, and f, which is the frequency, is actually 1 over the period, as you see here. So I'm gonna get the ratio between the time and the period, the ratio, and then I'm gonna multiply this ratio by 2 pi, and this is also another point here. This pi can be 180. Okay, so by this way, the ratio of the time divided by the period, you are going to multiply by 2 times 180 to get the angle here. Okay, so it's just what you did, you converted the time to angle. So that if the time is t, we're going to be 360. If it is a quarter, I will be here. If it is half, I am here. Okay, there is one more thing here. This pi, as you may know, this pi can be, if it is angle, so it's going to be 180. Also, pi can be 3.14, and in this case, it's called radians. Is that okay? So, as you will see right now in this question, I'm gonna ask you to convert the time into angle and also into radians. It's exactly the same thing. 2 pi ft. The only difference, and ft, as I told you, 2 pi t divided by the period. The only difference, if you put here by 180, you are gonna get degree in angle. If you put by here 314, you are gonna get it in radians, as you will see right now. So here I'm telling you we have a sine wave, and this sine wave is offset by 1/6 cycle. 1/6 cycle. Okay, so shifted by 1/6. Okay, so actually so actually here, this cycle means it's a period. So actually it is shifted by 1/6 of the period. Okay, t. This is the time. So the time is 1/6 t. Now I want to convert this one to degree and to 2 radians. So look what I'm gonna do right now. What I'm gonna do right now, it's 1/6 of the cycle. So it's gonna be 1/6 of 2 pi, because everything, the whole cycle from here to here is actually, this is a cycle. This is a complete cycle. Okay, so they told us 1/6. Okay, so all what I'm gonna do, I'm gonna say it's 1/6 times 2 pi. Now, if you put pi here, 180. Okay, so actually it's gonna be 1/6 times 360, which is 60 degree. So 1/6 of the period or is actually 60 degrees. Okay, the other way, if for radians, if you want to get it in radians, is exactly the same thing. The only difference is that instead of pi is 180, I'm gonna put pi 3.14. That's it. So it's gonna be, as you see here, 1/6 2 pi. Okay, but this time pi is gonna be 314. So if I do the calculation this way, so actually in radius is gonna be pi, which is 314 divided by 3 radians, which is 1.046. Any questions? Okay, great. Now I'm gonna move to the next definition. In this definition, I want to make a definition for wavelength. So what is wavelength? Okay, you know, if you have here a sender, if you have a receiver, if you send the signal, the signal is gonna propagate. It's gonna move. Okay, it's gonna propagate. So the definition of wavelength is the distance. Very clear. Wavelength means distance. Meter, micrometer, distance. Okay. So the wavelength is the distance the signal is gonna propagate in time t. T is the period. Okay. That's it. So the definition of the wavelength is how much distance the signal is gonna propagate. So as you see here, this is a time small t, as you see here. So after t plus the period uppercase t, the signal is gonna propagate. This distance, the distance propagate in time t, capital T, this is what we call wavelengths. Okay. So, and there is a formula to calculate, very simple formula. So the wavelengths, again, wavelengths means distance equal speed times time. Time here is a period. Okay, speed times time give you distance, right? So it's a very simple expression. But here, so again, wavelength means the distance, propagation speed, okay, times the period. Okay, period is 1 over frequency, as I said before. What is the propagation speed? Okay, propagation speed is actually different from one medium to another. So it depends on the medium, how fast the signal can move. So it is actually it depends on the medium itself. So I can see here we have number one, what you should learn here. What is the meaning of wavelengths? This number one. Number two, how can you calculate it? Number three, you should learn that the wavelengths depends on two things. Number one, the frequency. Okay, so the higher the frequency, for sure, the period is going to be less. Okay, that means the wavelength is going to be less. Okay, so as you see here, so there is a relation between the wavelengths and frequency for sure, and also there is a relation between the wavelengths and the type of the medium, the type of the channel, the medium we have, because it depends on the medium. Is that okay? Any questions? Okay. Next topic, which is really very important, I'm going to talk about if you have a signal, I can represent this signal in time domain. I can also represent it in frequency domain. So I want you to learn what do you mean by time domain, frequency domain. Okay, time domain, that's what we have done all the time. So if you have a signal like this one, this signal is actually in time domain. So the x-axis here is time, and the y-axis amplitude. And this signal is going to show me how the amplitude is going to change over the time. Is that okay? Okay, that's what we know, right? The same signal, I can represent it in a different way. In the other way here, I call it in frequency domain. Okay? In frequency domain, as you see here, x-axis is going to be frequency, not time, frequency. Y-axis actually is going to be the amplitude. And the signal, this signal is going to be represented by a spike, as you see here, only one spike. Is this a spike at the frequency? So this signal is 6 hertz. So this signal is 6 hertz. So I'm going to go to a 6 hertz, and the amplitude is 5. So I'm going to make a spike this way, 6 and 5. That's it. That's what we call frequency domain. Until now, it's not clear how this is useful. It's very useful. I'm going to tell you how. But for now, you should understand I can represent the signal in time domain, or I can represent it in frequency domain. So all what I have to do here, just spike at the frequency of the signal and the amplitude. That's it. Okay? Any questions? I'm going to explain. You understand now the difference between time domain, frequency domain. Okay? Until now, I'm not expecting you understand how this is useful. So, but you will see right now, okay? Because actually, when you have only one signal, you are not going to understand why this is useful. But now, that's what I told you last time. What I told you last time, any signal is actually composed of many frequencies, right? Using Fourier, okay? For example, so in this case, it will be more useful for us to represent this signal in frequency domain. So let's see this example. If I have 3 signals, as you see here, 1, 2, 3 signals, okay? So I want to represent this signal here are in time domain. So I want to represent them in frequency domain. Okay, so as you see here, this signal here is DC. What is the frequency of the DC signal? What is the frequency? Zero. There is no frequency, zero. Okay. So that's why this one I'm gonna represent it here. I'm gonna make a spike at 0 and it's gonna be 15. Is that okay? Now let's look at the second one. The second signal, the red one here. So this one actually the amplitude is 10 and it's 8 hertz. Okay. How do you need? That's a very good question. Can you count? It's 1 second, so you can count how many cycles we have in 1 second. Okay, so I think you can find it's 8. I'm not gonna count. When you go home, count it, it will find it 8. Okay, because I give you here 1 second. For the other one, you can. It's very easy. The green one is actually 16. Okay, and it has to be double. It has to be double. Why? Because it's if you look here, in 1 cycle, when we made only 1 cycle here, the other one made 2 cycles. Frequency has to be double. So if I get 1 frequency, I can get the other one easy. Okay. Anyway, so now you can see this signal. I can represent them in frequency domain this way. For every signal, I'm gonna go to the frequency, and then I'm gonna make a spike to the amplitude we have. Okay. So you can see here. That's what we call frequency domain. You can see the frequency domain is more compact. This is a very easy case. Why? Because we have only 3 signals. What if we have 100 signals, 200 signals? You understand what I'm saying? It's going to be very difficult to. The time domain is going to be much more useful for us. You got what I'm saying? So anyway, what I'm saying, a signal I can represent in a time domain and frequency domain. Okay. What I want you to understand, the frequency domain is going to be very useful when the signal has many frequencies. Okay, and actually this is the case, as I told you before. Any signal, okay, is composed of many sine waves, as I told you before. Okay, so it's going to be very useful for us to work on this one instead of this one. Okay, and as you see, it's actually compact. It's just more compact, this one than this one. As I told you before, composite signal. And this is something really very important, very interesting, based on what Fourier found. Fourier found that any signal is actually composed of sine waves. Okay, so sine wave is actually building block for any signal. Okay, sine waves with different frequencies, with different phases, with different amplitudes. If I add them together, for example, I'm showing you this example here. Okay, I have here 3 signals. These 3 signals. Okay, if I add these 3 signals together at every time, so if I add the voltage here plus the voltage here, I put it here. So if I do here, if I add them, so I'm gonna get this signal. Okay, so this signal is composite signal, composite. Okay, there is a mathematical way. Given this signal, I can get the component or the sign, the component of this signal. Okay, also there is some hardware devices can do that, some software also can do that. So there are different ways, mathematical way, software, hardware. Get this signal, you can actually get this signal. Okay, guys, any question? Okay, I'm going to tell you something also here very important. We will need it later. So again, if you don't believe me, when you go home, you can just add the voltage here or the amplitude. You will get the signal shown here. Is that okay? One more thing you should understand. So why I make, you can see, can you see the dot here, the dot signal here, which is a square signal? You can see it here. Okay. Why I made this way? I'm going to tell you why. Okay, please understand what I'm going to say right now. So, and if you have a signal like this one, okay, so actually this signal, as I told you, it has many frequencies. Okay, if I add all the frequencies together, so I'm going to get this signal. That's what I told you, right? But this signal actually it has infinite number of frequencies. Infinite number of frequencies. And the reason for that is because there is a rapid change here and here. Rapid change. To do for this rapid change, we need to have too many frequencies. Is that okay? So what I'm saying, if you have a square wave like this one, in order to get the exactly square wave, so I should have not only three signals here, infinite number of frequencies. Is that okay? Luckily, okay, but as you see later, it's going to be too complicated if I want to work on an infinite number of frequencies, okay? So there are too many frequencies. But if you see here, if I just take three frequencies out of the infinity, if I just take three, so I'm going to get something very approximated. You can see here. So this one is going to be close to square. If you add more frequencies, this one is going to get closer and closer and closer to a square. Take a seat quickly. You understand what I'm saying? So what I'm saying now, I put only three frequencies here. So I got something very close to square wave. If you want to get something more accurate than that, so you have to add more frequencies. The more frequencies you add, the more this one will get closer to us. If you want to get an exact square wave, so you should have infinite number of frequencies. You know what I'm saying? Yeah. So, for example, if you have a signal like this one in time domain, so in frequency domain, I can make it this way. This one here, the frequency of this one is f. The frequency of this one is 3f and 9f. So we can make it this way. This is a time domain. This is a frequency domain. There is another important thing here you should learn, that there are two cases. If the signal is periodic or if it is not periodic, okay? If the signal is periodic, like this case, if the composite signal is periodic, so the frequencies we have here are actually discrete frequencies, discrete. You know what I mean by discrete, okay? So it's not continuous. However, if this signal is not periodic, so actually in the time domain, I'm going to have a continuous frequency, as you see here. Okay. So again, what I'm saying is that if the composite, now you should understand what I mean by composite signal. Okay. Anything other than the simple signal, this is a simple one, is composite. It's number one. Number two, what I'm saying is that if the composite signal is not periodic, so this one should have continuous frequencies this way, continuous. They are not discrete, continuous. This is a frequency domain of this one. Okay. But because this one is periodic, so it's going to be discrete, as you see here. It's going to be one here, and then one here, discrete. Okay, any questions? One more thing you should learn here in case of a square wave. This is a square wave, as I told you. In case of square wave, the first one here, the first one at f, by the way, the frequency of this one is f. So the first one here, which is this one actually, the first one is going to be frequency f. And then the next one is going to be 3f. Next, again, there is some mathematical way to convert this one to this one. Okay. Next one here is going to be 9f. Again, this is I took only three. Because but this is a square wave. In case it's a square wave, I should have an infinite number. But just for approximation, I only got three. Okay. So you should know the first one here, we call it the fundamental frequency, the first one. The other ones, because the other one is just multiple of this one, as you see here, 3f, 9f, multiple of this one, okay? So these ones, we call it harmonics. So we have fundamental frequency, which is f. The other frequencies here, we call them harmonics. These harmonics are multiple of f, okay? For example, because this one, 3f, I'm going to call it the third harmonic because it's 3f. This one, 9f. So this one is the ninth harmonic. Is that okay? As I told you, if I add more harmonics, this one will be closer to exactly a square root. Is that okay? This one here, if I add more frequencies, it's going to be, and at infinity, it's going to be exactly the same thing. Square root exactly. No, very simple. If the signal is periodic, don't think about it. If it is periodic, discrete right away. Okay, it's continuous. It's the frequencies are continuous in case of in the case of if it is not periodic. Okay. So, any question? So you understand now what I mean by time domain. You understand what I mean by frequency domain, what I mean by the fundamental frequency, and also what I mean by harmonics. You should also understand for a square wave, we should have an infinite number of frequencies. Also, in case of if it is non-periodic, the frequency has to be continuous this way. Any questions? Okay, so there is, again, I told you, so how frequency can be used, okay? One way, for example, if I have the frequency domain this way, I can learn a lot of things from the frequency domain. Listen to me. Number one, what I can learn here, I can learn the maximum frequency we have here. The maximum frequency we have is 40 hertz. The maximum frequency we have here is 40 hertz. Is that okay? Because I told you this one has a square, has a number of square waves. Sine waves. If you add all of them together, but for sure, because this one is continuous, it's going to be a very large number for sure. Okay, but I can learn from this one. The highest frequency here is actually 40 hertz. Okay, I can also learn, and this is very important, by the way. I can learn that the frequencies at the beginning and also at the end here, they have little amplitude, so they may not be that important. So you will, as you will see later, I can just ignore them, or I don't need them. You got what I'm saying? You can see here. So you can see here the frequencies in the very beginning, and at the end, the amplitudes. This range of frequencies, the amplitude is small, right? So if I ignore them, yes, I'm not gonna get exactly same signal, but should be approximated enough. You got what I'm saying? Should be close enough. Anyway, so now I want to make a definition based on what I explained, bandwidths. Okay, and the bandwidth is somehow tricky because there is a bandwidth for a signal and there is a bandwidth for a cable or medium. So this is a different story. Okay, but let's focus on this one first. If you have a signal and this signal has this frequency domain, as you see here, okay, for sure, because this one is discrete, so for sure this signal is periodic because it's discrete. Is that okay? So you can see here we start from 1000 and then we have frequencies until 5000. So if I ask you what is the bandwidth of this signal, very simple. The bandwidth is the difference between the highest frequency and the smallest frequency component of this signal. Okay, so in this case it's going to be 5000 minus 1000. This is going to be the bandwidth of this signal. Okay, again, this signal can be any signal, so it can be something like that, but inside this signal it has sine wave component, as I told you before, and this sine wave component, so they are going to be from 1000 to 5000. And the bandwidth is actually the bandwidth for the signal, the difference between them. Same thing here, but as I told you, if it is continuous, if the frequency is continuous, so this means if the frequency is continuous, so that means this signal is not periodic. Okay, and it's the same thing. The bandwidth here is the difference between the biggest frequency and the smallest one. Any questions? Good. So let's have some examples here based on what I explained. Very simple example. So let's start with the first example here, a periodic signal, very important. So when I tell you it's a periodic, and then I ask you to draw the frequency domain, so it has to be discrete. Okay, that's why I'm telling you here a periodic. So a periodic signal has a bandwidth of 20. So the whole bandwidth is 20, okay? And then I'm telling you the highest frequency is 60. So Here, the highest one is 60. And the whole bandwidth from here to here is 20. So what is this frequency? The first frequency, what is this? It's gonna be 40, 60 minus 20, right? So yeah, so here I start from 60. The whole bandwidth is 20. Okay. So from here to here so this one should be 40. Yes, so I got this one and I got this one and I know the bandwidth. And then the question is telling me the spectrum, or we have all frequencies of the same amplitude. Okay, so that means we have 40, we have 41, 42, 40, because that's what they are telling me in the question. We have all frequencies. So it's gonna go all the way here, and all of them have the same amplitude. So that's why I was able to draw the frequency domain. Any questions? What is that? Okay. Let's have another question here. I'm saying non-periodic signal. Non-periodic, so it has to be continuous right away. Okay. So it is non-periodic, and then I'm telling you the bandwidth is 200 kilohertz. And here I'm telling you the middle frequency is 140. Again, so here I have some frequency here. I don't know this one. I don't know this one. All what I know the bandwidth. So I know from here to here. I know from here to here is actually 200. Is that okay? The difference is 200. And then he's giving me the middle frequency. The middle frequency is actually 140. Is that okay? So because this is a middle, so actually from here to here should be 100. Sorry. And also from here to here should be 100. Is that okay? Because this is in the middle. So this is in the middle. From here to here is 200. This is given to me. And the middle is 140. So from here to here should be 100. And from here to here should be 100. Okay. So 140 plus 100. So this one should be 240. And 140 minus 100. So this one should be 40. Is that okay? So he's giving me the middle. He's giving me the, he's giving me the middle, and he's giving me the bandwidth. And because this is the middle bandwidth, so I know this one is 100 and this one is 100. Is that okay? Also, in order to be able to draw this figure, also I have some information here. The two extreme frequencies have amplitude 0. Okay, so also here the extreme frequencies, these two frequencies, the two extreme ones, they have amplitude of 0. So we start here from 0, go this way. Okay. Any questions? Yeah, in the question I'm asking you to draw the frequency domain. Okay. So again, if there is something like that in the exam, number one, what is important is that number one, is the frequency continuous? I just wanna know. I wanna know if you know if this one is non-periodic, so it has to be continuous. Is that continuous or discrete? For sure, I'm gonna look at these numbers. Okay. And then you should draw it based on the information. It's telling me the amplitude is 0 here and amplitude is 0 here. Okay. Any questions?
The extreme amplitude, like for example, 4. So it would be a straight line, and then the rest, and then a straight line, right?
What is that?
If let's say it's not, the extreme is not at 0.
Yeah. So
it's a straight line.
Yes. So for example, if I tell you it is, for example, 5. Okay, so it's gonna be here 5, and here 5. Yeah, it's gonna go this way. Okay, so in the coming section, I'm gonna focus on digital signals. Okay, so here, so this is a digital signal. As you see here in this signal, we have two levels, either 0 or 1. So we have two levels, 0 or 1. I'm gonna use one level to 1 and one level for 0. For example, 5 volt and 0 volt. 5 volt is gonna be 1. 0 volt is going to be 0. Okay, so this is 0, 0, 0, so it's going to be 0 volt, 0 volt, 0 volt. So I have two levels, whatever the values of, it doesn't matter what are values, these values, but I have two levels. Okay, I'm going to take one level to represent 1. I'm going to take another level to represent 0. Is that okay? Okay, so this is for sure, this is a digital signal. I can do it in a different way. I can do it in a different way. Okay, so if I increase the number of levels to 4, so I have 4 levels. Is that okay? So actually, every level can represent 2 digits. Okay. For example, as you see here, this level number 4 is going to be 1, 1. So every time, again, look here. If I have 2 bits, okay, how many numbers I can represent in 2 bits? 2 to the power 2. So in general, if I have any bits, I can represent 2 to the power n. Is that okay? It started from 0, 0, 0, which n zeros, until 1, 1, 1, 1, which is n ones. Is that okay? So, so in case of 2 bits, so I have 0, 0, I have 1, I have 2, I have 3, this way. So I have 4. That is why, in case of 2 bits, I need 4 levels. Because every sequence here, or every number here, should be represented in 1 level. You understand what I'm saying? What I want to do right now, I want to get a relation between the number of bits and the number of levels I need. But let's finish this one first. So if you see here, now I have 4 levels. Okay, so this level, I'm going to take it for 1, 1. This level, I'm going to take it for 1, 0. This level here is going to be for 0, 1. Okay, so I need 4. So this one is going to for this one, and this one here for this one, and 0, 0 is going to be this one. That's it. So every time I have 0, 0, I'm going to use this level. Every time I have 1, 0, this one here, I'm going to use this level, and so on. Is that clear? Okay, great. So now I want to get a relation between the number of levels and the number of bits. Okay, represented in every level. Very easy. The relation is, if you have n bits, so actually number of level I can have 2 to the power n. If you use a number of levels, okay? So if you have 2 to the n, this one I'm gonna this is how many levels I can have should be 2 to the power n, okay? But if I want to calculate if I want to, so n here, how many bits I have? L, how many levels I have, okay? So, you know, if I take the log for the 2 sides, so it's going to be log 2 to the power n equal log 2 of L, okay? And you know this n can go outside, so it's going to be n log 2 of 2 equal log L, okay? Log 2 of 2 is 1 for sure. So actually, so the number of bits should equal to number of bits should equal log 2L. Okay. So again, very simple. What I'm saying is that if I have any bits, so for any bits, I can have up to 2 to the power n levels, right? Because every number should be 1 level. Okay. Or the same thing, if I have here L levels. If I give you L levels and I tell you how many bits can be represented in these L levels, you can just take log 2. It's exactly this one similar to this one. Any questions? For example, let me give you one example. For example, you know, if you have 2 bits, so the 2 bits, I can 2 bits, so I can have up to 2 to the power 2, which is 4 numbers. Okay. If you take log 2 of 4, it's going to be 2. Okay. Same thing, if you have here 3 bits, how many numbers can be represented in 3 bits? 2 to the power 3, 2 to the power 3, which is 8 levels. If you take log 2 of 8, give you 3. So anyway, so here we have a relation between the number of bits and how many levels we can have, okay? This is just a very simple example. And this example I give you, we have 8 levels. Here I tell you we have 8 levels. So, and then I'm asking you how many bits we can represent here. So all what you have to do, just number of bits equal log 2 of 8, which is 3. Is that okay? So if I have 8 level in every every level here, I'm gonna represent 3 bits instead of 2. Here, 2. No, it's 2 because I have 4 levels. I can make this one 3. But if you want to do that, you have to increase the number of levels to 8. Okay. Also, there is something interesting here. For example, here I'm going to tell you, what if I have 9 levels? It's interesting because this 9 is not 2 to the power of something. Doesn't give you 9. Okay. So let's see how it works. So what happens here is that now I have 9 levels. Okay. And how many bits we can represent it there? As I told you, I'm going to get log 2 of 9, which is equal 3.17. So I need 3 bits and 0.17 bit. Does it make any sense? 0.17 bit? The answer is no, right? So in this case, actually, you have to round this one to 4. Okay, so you have to round it to the ceiling. So this one. So in this case, I need 4 bits. Okay, and actually the 4 bits is going to give you 16 levels, but I'm not going to use the whole 16. Out of the 16, I'm going to use 9. If you round it to the floor and you make it 3, it's not going to work, because 3 is going to be 2 to the power 3, which is 8, but I need 9. You got what I'm saying? So I'm going to take the bigger one, because that's how it is. We have 8. After 8 is 2 to the power 3. After 8, we have 16. Nothing in the middle, right? So either 8 or 16. So I can take the bigger one, and also I have 16 levels, but I'm not going to use all of them. I'm going to use just 9 out of the 16. Any questions? Good. Also, there is a definition I want to make it here. In the analog signal, we define frequency. I defined frequency before. Here, most of the signals we are going to use in the digital signals, most of the signals are not going to be periodic. Okay, so they have no frequency. Okay, because they're not periodic. So instead of frequency, instead of using the term frequency, I'm going to use another term, which is, we call it bit rate. Is that okay? What I'm saying, in case of because the signals we are going to use here are not periodic. Okay, so there is no frequency here. Instead of frequency, we are going to use another term, we call it bit rate. And bit rate means how many bits in 1 second, the number of bits per second. So from here to here is 1 second. How many bits you have? 1, 2, 3, 4, 5, 6, 7, 8. So this actually is going to be 8 bits per second, as you see here. 8 bits per second. Okay. If I look at this one, what is the bit rate here? Okay. So you can see here 2, 4, right? 2, 4, 6, 8, right? 10, and so on. You can find it is 16 bits per second. Any questions? Okay. There is something very interesting here. Okay. You can observe here, when I increased the number of levels, I actually also increased the bit rate, right? Here I use 2 levels. Here I use 4 levels. By increasing the number of levels, actually I increase the bit rate, which is something very desirable, something very good. You increase the bit rate. You got what I'm saying?
Isn't that more space?
So I'm gonna ask this question, but in a different way. So, okay, this is good news. So why you don't make it 1 trillion levels? In this case, we can transmit too many data in a very short period of time. Everybody will be happy if you do this way. Unfortunately, there is a limitation. We can't do that. The limitation is hardware limitation. The limitation is the more levels you have, it's going to be more difficult for receiver to differentiate. I need more complicated hardware to differentiate between the different levels I have. You got what I'm saying? So let me summarize what I said. Number one, the more levels you have, the more the bit rate, which is very good. However, it's going to be more complicated for there is a limitation. If there is no limitation, we would be happy. You can just increase the levels. I can transmit too much data in a very short period of time, but there is a limitation. The limitation is at the hardware, at the receiver, okay? The more levels we have, the more difficult it is to find it. Okay? I have several examples here to explain more the idea of bit rate to understand it better. So here in this example, I want to download a document. And this document actually is going to have 100 pages per minute. 100 pages per minute, and then I'm gonna ask you what is the bit rate I need to download it. Okay, look how I'm gonna do it. Number one, I have 100 pages. Is that okay? Per minute, and for every page, I'm gonna assume we have 24 lines in every page. Okay, every line I'm gonna assume I have 80 characters. Okay, every character using ASCII code. Every character, we're going to have 8 bits. So this one is going to give me, why I did all of that? Just, I need to know how many bits I have. That's it. You know what I'm saying? So now I'm going to see how many pages, how many lines, how many characters. So this one is going to give me how many characters I have in total. Because this is a character per line times the number of lines times the number of pages. Okay. So this part here is going to give me how many characters I have. If I multiply by 8, because you know in ASCII code every character is represented by 8 bits. So here this one is going to give me the number of bits. Okay, the number of bits. But there is something tricky here. I think it's a mistake from in the book. This is per minute. So if you do the calculation here, what I'm going to get here, I'm going to get bit per minute because it's given to me in minutes. Okay. If you want to convert it bit per second, so you have to divide this one by 60. Okay. Because this is actually the number of bits in 1 minute. If I divide by 6, it's going to give me the number of bits in 1 second. No, this is how many bits in a minute. So you have a minute. Okay, this is the number of bits in 1 minute. So I have to divide it by 60 to give me the number in 1 second. No. This is the number. This is the number of bits in 1 minute. You got what I'm saying? So if I need a second, I have to divide, not multiply. If you multiply, so I'm gonna make it hours. Anyway, let's move to the next example to just a bit more understand the idea of bit per second. Here I'm telling you I have a voice signal, and this voice signal has 4K hertz. Okay, and I'm gonna convert it from analog to digital. I'm not sure if you are familiar with this one. So the idea here, when I convert it from analog to digital, so I'm gonna take 2 samples. In every cycle, I'm gonna take 2 samples, 1 sample here and 1 sample here, and then I'm gonna convert these 2 samples. Okay, so we need to sample the signal twice at twice highest the rate. That means 2 samples per hertz. So I need to take at least, this is for sure you can take more if you want to make it more accurate, but at least you need to take 2, 1 here and 1 here. Okay, so now, and each sample is going to take 8 bits. Okay, so this one is going to take 8 bits, this one is going to take 8 bits. So I need to know what is the bit rate here. So again, let's see here. Number one, the frequency I have is 4K. Okay, 4,000. Okay, in this 4,000, I'm gonna multiply it by 2 to give me the number of samples. Because in every cycle, I'm gonna take 2 samples. Okay, so I'm gonna multiply 4,000 by 2. 4,000 by 2 is gonna give me the number of samples. Every cycle, 2 samples. Okay, then every sample I'm gonna multiply it by 8, and this actually gives me the number of bits per second. Okay. Let's have one more example, very interesting example. For example, it's telling you here in high definition TV, HDTV, in high definition TV, we have, in TV, we have frame, we have picture, right? Image, and we change this image 30 times per second. So every second, you know, the animation is just pictures, right? Picture, you just present, you just show these pictures, okay? The rate is going to be 30 times, so 30 pictures per second. Every second, I'm gonna use 30 pictures, okay? Every picture is gonna be actually 1920 times 1080 pixels. These are the number, you know, any picture has pixels. So this actually 180, and from here to here actually is 1920. Is that okay? So if I multiply these two together, this one is gonna give me the number of pixels in one image. But okay? So this is number of pixels in one image. If I multiply it by 30, so this one is gonna give me, okay, how many pixels we have every second. Because in every second, I'm gonna have 30 image. Every image is gonna have this number of pixels, okay? And every pixel is gonna take 24 bits. You know why every pixel takes 24 bits? Because every pixel actually is gonna be represented by 3 colors, RGB, right? Every one of them is gonna take 8 bits. 8 times 3 is 24, okay? Again, every picture is going to have this number of pixels, okay? When I multiply it by 24, it's going to give you the number of bits per image, one image. If I multiply it by 30, now it's going to give you how many bits in total, how many bits in 1 second, right? So if I do this calculation, I find I should have this speed for this TV, for this kind of TV, I should have this speed. But actually, we don't do that, because we usually use compression, because you do compression and you decompress the signal. So actually, we can reduce it from this number to this number. Any questions? Yeah, because I'm gonna use less bandwidth, less communication. You get what I'm saying? It's similar if you have a file and you compress it to take less space in your hard disk. Okay, so when you compress it, it's gonna take. I need less communication, which is good. For sure, the problem you need to do computation. Any questions here? No, I'm saying practically they do that. Okay? Yeah, but it depends. This reduction, it depends on what technique you are using for compression. It depends if you have enough computation, if your CPU is strong enough to do the compression, decompression in a short period of time. The last thing I want to teach you before we take the attendance is actually the bit length. Okay, there's a definition, it's called bit length, and this bit length is exactly similar to the wavelength I explained before, the wavelength. But here in case of a digital signal, we call it bit length. So it's exactly the same thing. So if you have a bit length, it's gonna be the distance this bit is gonna take in the medium. When you is exactly the same thing. But we use wavelengths in case of analog signal. In case of digital signal, we use bit lengths. Okay, so actually the bit length here is equal to propagation speed times the bit duration. The bit duration times the propagation speed. Is that okay? So this is equivalent to the wavelength, but wavelength for analog signal. Okay. The last thing I want to say here, and I think I already explained it. If the signal is periodic, so you are going to have discrete frequencies this way, okay? But if the signal is not periodic, you are going to have continuous frequencies this way, okay? That's what I explained. Any questions? Okay. Let's take the attendance. 2536. Thanks. Awesome.